Now we are going to discuss about the basic flow and the control volume. We already discussed it before, the material derivative, which is if I have a particle and I need to check the field, which is we discussed it before regarding the velocities and the acceleration. Acceleration is on a particles and which is the forces on a particle, and we need to convert it to fields because our velocity equation is fields. Okay, so we use the material derivative to convert from Lagrangian descriptives to Eulerian from Euler, this descriptive or descriptions. Okay, and we make the differential analysis and the material derivative technique. Okay, to define or to derive or to write the full Navier-Stokes equation, if we remember. Okay, for the part of the acceleration. Now we need to discuss something else, which is system analysis and the control volume analysis. System analysis is a closed system, no mass cross the boundary. It is a closed system. Okay. Uh, a control volume is an open system, which is masses can cross the boundaries. Okay, what is the problem? So it was the systems. No, there is a problem. If you have an interaction between in the boundaries with the masses, so some or a lot of external component or external side effect on the entire system going to change. We are using some technique named Reynolds Trans Transport Theorem. It is an integration analysis. Okay, what is this? Okay, if a probability like B, B, any probability divided by the mass, we name it as probability dot. Okay, so if we have a control volume, which is an open system, there's flow in and out. This is a Reynolds transport theory, and later on we'll understand what is beneficial, what is the benefit of it. Is stating that if you know this probability and you want to check what is the change of this probability in time, it is the full integration for or the integration of the control volume, which is mean for the entire control volume, the change of the density or the partial derivative of the density, partial derivative of density multiplied by the rate of that function by the mass multiplied by integration in the entire volume, which is another case. Take a small slice of the volume and check. It is very simple, huh? That probability per mass, that probability per mass, what is the rate of change of it by time multiplied by del small of density. Okay, this for the control volume plus integration of control surface. Okay, this for the entire volume. So for example, if you have one rectangle like this is for the entire volume plus the surface of the boundary, only the surface, not the entire, is integration for the surface, control surface, rho multiplied by the probability per the mass multiplied by the velocity vector. What is the change in the velocity? And of course, this is n, which is magnitude is equal 1, which is how much here is because you make integration. So here is 1, here is minus 1, here is because that's why in vector. Okay, so the direction of the velocity. Okay, multiply by the area. In another way, if you can get it, this one is a mass flow rate outside, and this one is the change of the density inside. That's it. This is the Reynolds transport. It is very logic that the change of that property in time is the rate of change of the density multiplied by the property per mass, because this is the rate of change of the mass, plus the rate of change of that property per mass multiplied by mass in and mass out. That's it. Okay. This one, if it is fixed control volume, it will become a little bit complicated now if it is not fixed, which is mean the control volume is moving with me. It's not fixed in one location, so it is moving with me or changing in the shape. For example, it was like this, then become like this. In the same location, it's changing in the shape, or it is moving. Okay. What is the definition of it? It is the same concept. It is d by dt, but we put it outside, or dv, etc. plus same. But remember that here the velocity become relative velocity. It is the relative velocity. Now, because the velocity is moving, or the control volume is moving, it's okay. But here is the velocity should be relative, which is mean it is the velocity magnitude, or the velocity vector, minus the velocity of the control surface itself. So if the cube is moving like this with velocity 1, and I have velocity like this equal to, in this direction equal to, so the relative velocity is 2 minus 1. That's it. 2 minus 1. Okay, this is the relative velocity. Okay. And by the way, this is control surface, which is mean that is why deformation is okay, because for example, this when it is coming bigger, only this surface going here, and the other velocities is relative velocity is the velocity because it's not changing, only this deformation of the control surface going bigger. So you need to check what is the relative velocity here to that surface only. Okay. Okay, agreed. This is very simple, very easy. Okay, what does it mean? Now is the assumptions, which is going to give us what is beneficial points. For steady flow, we know dt bye bye. So all of this term is bye bye. All of this term is bye bye. No change in the time. So any change in the probability in the system divided by the time, when you're doing integration, closed integration, which is mean for the entire closed surface or control surface, and you write what we agreed, it is equal to this one. Example, give me an example. You have a two tanks, and the two tanks having whatever here inside. Okay, okay. You know, or you want to get what is the probability of anything changing in the time for the entire closed surface. You already make controlled volume here or controlled surface. Okay, it is what it is, in and out, in minus out. We agreed that control surface is what? Control surface here, it is in and out. That's it. What is mass in? What is mass out? Because if you have two, what in, what out, each surface. Okay. So it is sigma out, rho, b average, whatever is at the out, because you know at the out maybe the velocity is not equal. For example, as we discussed it before, the velocity can take in the pipes this shape. Okay. So V average, whatever is the V average is, but which is represent the magnitude of integration of all of these. Okay, multiply by the area. This is equal minus out. So okay, and you just need to know that V average, as we discussed, V average, because the flow here is zero, flow here is zero, and it's coming bigger, 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 and the peak here, B average. Okay. In these techniques, we don't care about each velocity itself. We are taking care about the entire system, the entire control volume, the entire control system. Okay. 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 Now let's go to, still all of this is the definitions. I didn't write what is the properties, what is the velocities, what it is, just the definitions. Later on we'll get understand. Okay. For a system, for a conservation of mass, d mass in the system by dt should equal zero. This is a law. Apply Reynolds transport. So dB by dt, which is d mass by dt, should equal zero. Write the transport theory, or the Reynolds transport theory. So I just write it. No b, write m. No b, write m. M over m is 1 because this is b small, which is b over m. Okay. So it will be 0 equal d by dt, sigma control volume r dv, multiplied by, of course, this is v dot term, which is means volume flow rate, because this will become mass flow rate. Okay. Rho vn, etc. And this is the equation of conservation of mass by applying Reynolds transport, which is mean the change in the mass in the system is equal to the change in density, the rate of change of density, multiplied by the how much the system absorb mass and increases the density, and how much the system losing flow rate outside with the mass and getting flow rate inside with the mass. Okay. And then, as we discussed before, is the direction, and this is a conversation of mass. Okay. Uh, just a small example, but it is very silly, but it's okay. Imagine that you have very slow flow, which is means the temperature is not change. It is, and you're filling a container. So applying the conservation of mass, this one is sigma m in and m out, as we agreed. And while we are taking the control system, if I took the control system all of here, there is no mass in all the wall except here, which is will make our life easy. So this method, when you do for all surfaces, and I know that is a container, all surfaces closed except here, so I only have one surface, which is very easy for me. And this for the volume itself. Apply sigma in, sigma out, which is equal to this one. It's very simple. We can put that is the change, the rate of a change, because uh, the volumetric flow rate in or out or whatever is not a function of the density. Density is going to change, by the way, but it's not a function of dv. So it is d rho by dt, control volume, equal to mass flow rate. Okay, integration of control volume one slice for full slice is the volume, by the way. So d rho by dt equal mn by dv, because there's no m out. So from rho to rho naught, it is just an integration, by the way. From rho to rho naught, it is equal to m dot v dot by t, which is rho minus rho naught, which is d rho, approximation, of course. Delta rho is equal to mass flow rate divided by volume flow rate multiplied by the time. It is very logically simple, يعني it is, but it is how we're going to use that integration complication formulas to get very simple logic formula, but it's going to help us to imagine. Uh, we are going to discuss what is the actual beneficial of Reynolds transport when we are dealing with closed systems and open systems, okay? And we cannot use Navier-Stokes because Navier-Stokes applying what is the fields look like. But when I need to know what is the entire flow, what is the full velocity, what is all of these items, which is okay, how is it going to be? You need to make the integrations or you need to use Reynolds transport for the entire system. So this is two ways. I need to know what is the fields, or I need to know what is, for example, heights, velocities, pressures as a full, like for example, what we discussed here, the forces, one of the ways to get what is the forces to, if I know the velocities, of course, I to make the integration, what is in, what is out, etc., etc., etc. But because I don't know the velocities, I just got it here, so we forced to follow with the forces to use uh, the potential function. So to sum up, Navier-Stokes fields give you functions, potential flow series, theorem, giving you way to write also the velocity fields, and from it you can approximate some of, or you can calculate some of the function. But in ideal cases, in case of you have, you need to know what is. Don't use the derivative method, use the integral method if you know the control system, which is mean you know some boundaries and it is closed or it is very simple to apply that theorem, like tanks, pipes, which is mean it is entire closed. Remember in the potential flow and the Navier-Stokes, we never open subject like I have a tank and a pipe and I need to check what is the fields. I can do it, but it is much easier to use a control system rather than this. And if you're trying to apply the control system, for example, a pipe and a sink and a big tank, what is your control system? You have a lot of surfaces, and this surfaces is not a boundary, it's not a wall, which is you you need to calculate in and out in each surface, which is not defined. So it is wrong direction to follow control surface. Okay, so when you have a confined areas like a tank filling, water tank and pipes, something like this, use a Reynolds transport theory. If you have some certain types of flow pattern, and you know how much the flow rates for that types of flow, combination of it, you need to use potential flow theory. And if you know a boundary condition enough, use the Navier-Stokes. So first Navier-Stokes, if you have boundaries condition, which is you can define about something, then if you have no a type of flow, which is very open, and you can approximate that type how it look like without a real boundary condition, you have really no boundary condition, maybe one or two maximum, so go with potential flow theory. But if you have a fully closed system or a semi-closed system like tanks, etc., use Reynolds transport. Okay, this is how we are going to think, how we are going to decide what we need to do. This one is other basic, but we're going to use it. It is definition. What is the friction loss? Friction loss of head loss is equal to F L V square over 2 d hydraulic, or the hydraulic diameter multiplied by G. I think so. It is very fundamental, very basic. Yeah. It is for pipes only if Reynolds number less than 2000. It is laminar and transient. It is from 2000 to 4000, and turbulence so it's over 4000. I think so. We all know what is Reynolds number. Okay. Reynolds number is it is a relation, or it is what is the inertial force divided by the viscous force. Okay, and hydraulic number, this one is A plus B. Okay, I will just remake it again. Okay, now the friction coefficient of friction F, you can use Moody chart, or you can use this equation, which is 64 for the laminar over Reynolds number, and for turbulence for smooth pipe is 0.316 over Reynolds number over 1 over 4 for turbulence. And if you know epsilon, which is the roughness, epsilon is the roughness, and this one is if it is transient, and you know epsilon is the roughness coefficient or reference number. If you are going to use Moody chart, you will find something named R. You know, Moody chart, we already know it, huh? Which is absolute roughness, which is epsilon divided by D. Okay. Okay. It is very simple. For example, if we have a pipe and there is a rod inside, so the hydraulic diameter is 2a minus b, and a and b is radiuses. And if we have a hydraulic diameter for square, it is a, and if you have a hydraulic diameter for a rectangular, which is a and b, it is 2ab divided by ab square. Okay, which is the squares. Okay, which is the main equation is this one. I think so. It is very simple. It is not that big deal. It is 4a, or 4 times of the area divided by the parameter. This is the equation. Okay, and this one a plus b. Sorry, a plus b. Okay. For fittings, it's just also you need to know it for any fittings. Delta B, it is k. K is a constant for the fitting divided by rho over 2 multiplied by v square. If each fitting divided by rho g, so that's it, and square of as well. Just an indication of general concept. Okay, we're going to use it. Okay. Okay. This is, we need to identify it ourselves. Do we know the thermodynamic or no? And we need to understand this one very well. Okay. This forms the thermodynamic. Okay. We need to know it. However, I am going to identify it. See, sigma qn, or what is energy in and out to the system, what is the shaft power in and out to the system, for example, what is I'm doing work to it, what I'm in and out, and what is energy in and out, should equal by anyhow what is the change of the energy, rho dV, and in the control volume and in the control surface. This is the kinetic, this is the potential, and this is the enthalpy. Okay, which is the internal plus the pressure energy, the enthalpy. Okay, which is specific enthalpy. Okay. We noting that is when we are using velocities, here is the velocity average, and when you're using rho is the rho average. However, we need to calculate exactly what is the rho average, what is velocity average. Okay. If we are going to state that is steady state, so this term is bye-bye. So Qn minus Q out plus work in minus work out equal to the change of, as we agreed before, of mass multiplied by, because this one is a mass, this is a change of the mass. Okay, multiply with what? Multiplied by the enthalpy, which is this term, plus the kinetic energy plus the potential energy minus this one. By the way, this is the first law of thermodynamic, but without these two terms. Okay? Because we assume that the kinetic energy is neglectable, but this is a general term which is coming from Reynolds Transport Theory. Okay? So from Reynolds Transport Series, we can derive the first law of thermodynamic. Okay? Okay, now we need to understand that is velocity is an average and V average, it is depending, is it laminar or turbulent? So for a small approximation and an accepted approximation that you can state that V average is equal to, or the kinetic energy is equal to V peak multiply a function. Okay, so or multiply a factor. So V average is a factor multiply a V. So whatever is the factor is, okay? And we name it is kinetic energy correction factor because the shape here is not equal, okay? The definition of the kinetic energy potential factor, it is 1 over A is area, integration from the entire area, D area, U, which is velocity by U V average, cube. This is the definition of it. Okay, we're going to do it? No, forget it. Already there is an approximation because this way is an approximation, so we can get the approximation directly. If it is laminar flow, which is Reynolds number under 2000 for pipes, for example, it is 2. And if it is turbulent flow, it is from 10.04 to 1.1111. Depends on Reynolds number, however, take it 1.05. Okay, this is an accepted approximation. Okay. Okay, now we can rewrite for the pump flow. Imagine that you have a pump. You don't care what is inside the pump. You care that the pump having an inflow and outflow, and you know there's some heat going out and in. No, there's no heat out and in, but you know that there is a shaft power giving in, but there's no shaft power giving out. Good. And you know there is a mass flow rate in and mass flow rate out, which is as we described here. Mass in multiplies this one, mass out plus this one. Okay. For Reynolds transport, put the numbers, put everything. Okay. So this is the equation. Then we can write that is work net. Okay. Divided by why I'm going to state it why we're trying to divided by gravity and m dot. So I just put m dot here and gravity. Then it will be b over rho g plus kinetic energy plus the potential energy. Okay, which is z. Okay, you will tell me, okay, where is u? Where is u? Where is the internal energy? Where is the internal energy gone? Okay, we know all of this is in Salvi, specific in Salvi. Okay, where is the internal energy gone? I told you, wait, I didn't put it out. I just put it out. Why I'm trying to write it in this way? Because it is Bernoulli. So work plus pressure energy, kinetic energy with correction factor plus potential energy equal to work plus this one equal to after the pump the pressure energy, velocity energy with correction factor and z, which is potential energy, plus the loss in the internal energy plus the internal the energy because it is an energy, so the losses or whatever it is something you put it injected in the heat, for example, fraction of which is mean whatever you're going to put in the shaft power, it will never going to be the full pressure and kinetic energy and potential energy injected in the fluid. So if the pump giving it 10 kilowatt, so the entire energy in the fluid never be 10 kilowatt. We have an hydraulic efficiency, we have the friction, we have the mechanical efficiency, etc., 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 which is derives this term. How much energy has been distributed, injected inside the water as an internal energy. Okay, then we're going to ask ourselves about the Q, uh, which is has been injected because the shaft going to give it some heat here. So when go like this, it will be minus. Okay, and this one we name it irreversibility, which is the irreversible work which has been done, which is you can never gain it back again. It is gone, but it was injected inside the fluid, and we name it also H loss. So we can write it like this. That is the work multiplied by eta. It is the horsepower or whatever we're going to have. And for pump, yeah, it's the head of the pump. So if I assume a work divided by g m square or m dot, it is head. Now you got it. And b over rho g, it is a head, and this one is a head, and this one head. So I can write that head plus head plus head plus head equal head plus head plus head minus head loss. So the head of the pump is equal to the work of the pump multiplied by eta pump. And if it is a turbine, so it is divided by eta turbine. Okay, but remember, if it is turbine, this will should be in negative. Okay, which is we can write pressure head, kinetic energy head, plus Z, which is head, plus H pump equal plus H turbine plus H loss. This is Bernoulli. So this one, how we can derive Bernoulli equation from Reynolds Transport Theory. From Reynolds Transport Theory, how we can derive the Bernoulli equation with all its function. This one, but how we are going to select our control volume. This is very simple. Okay. Okay. This is very simple example, but we need to see when you're going to write or put your control volume. Please don't make your control volume cutting here. Try to cut it from a certain velocities or a certain surface, and the other surface is a pipe. This is the first. Second, your control volume, try not to keep it inside, keep it outside, because no viscosity. It is okay because in the control volume they don't care about whatever inside. This is the beauty of the Reynolds transport. Put the control volume anywhere. But remember, don't cut pipe like this. Or you can, by the way, but try to put, because here pressure is zero, pressure is zero. Be smart. And also don't make it inside the surface because you need to take account the viscosity. Okay? So you can write this one. Imagine if you're going to have any other shape. Okay? Okay. We're going to have very quick example. It is lengthy calculation, but it is very simple, straightforward algebra. There's no integration going to be happen because we already derive the equation of Bernoulli and we're going to use it. Okay. Specific. Somebody told you that the specific gravity is equal 0.9, which is mean O is equal 900. Flow rate is equal like this, or he want the flow rate to be equal like this, and he told you how much is the height should be. Then he told you this is a diameter, which I have, this is the length of the pipe, which I have, and this is the head, which I have. Okay, so it is very simple. Make the boundary, see the boundary, I took it outside the pipe, and from here inside no problem because the velocity is almost neglected. So when I have area, I can get the velocity. When I have the velocity, by the way, I can get the Reynolds number. Why I need to get the Reynolds number, I will tell you to define alpha, which is a kinetic uh, uh, correction factor. Of course, alpha at 1 is equal to 0 because the velocity is equal to 0. Alpha at 2, we need to calculate it, Reynolds number, blah, blah, blah. When you calculate the Reynolds number, we need to know mu. Sorry. The question is not what is the height. The question is based on this condition, what is the mu? This is the way of testing the mu, by the way. This is a way of testing or to if you have an oil and you want to calculate, or in the lab you need to calculate what is mu, what is the viscosity. You will check what is the flow rate, you check what is the height, you know what is Reynolds number, but mu, it is a function of mu. You will put everything, you don't know what is phi, bear with me. Then we would, you will find the friction, the coefficient friction factor. By the way, it is H loss friction factor. Friction factor is equal like this from the H loss. H loss we get it from Bernoulli, by the way. So you get friction factor equal blah blah blah. Okay, now we are going to take two cases. You will assume that is flow here is laminar. So if the flow is laminar, our observation here is for alpha is 2. Plug the numbers, so mu is equal like this. From this mu, go to here, put mu in the number what you have, calculate, then you will get the Reynolds number is 957. Because it's 957, it is less than the 2000, so our assumption is correct. And based on that, you can calculate the friction coefficient factor, the coefficient of friction, and based on the coefficient of friction. Sorry. Now we are going to check if it is turbulent, and of course a smooth pipe. So if it is a turbulent flow, the coefficient of friction is this way, by the way, and here is the coefficient of friction with this way, by the way. So we have a function between coefficient factor, coefficient of friction and mu, same concept. Assume it is turbulent. When you assume it is turbulent, you will use alpha is 1.05 in this one. So you will get mu, apply mu in Reynolds number. You will get what is the Reynolds number will be. It is 1200. 1200. When it is 1200, it is less than 2000. Our assumption, our case is turbulent, and it is less than 2. This assumption is wrong. So this answer is correct, and mu is equal to this number. If you need to kinematic viscosity, it is divided by the density, it's okay. And based on that, you can write what is really head loss. It's like this. And by the way, this kinematic viscosity is like this. And we use 2 for alpha because it is laminar. This is a way of calculating. Okay. Now we will go to the next example. Next example, there is rod in the middle. It is just to write. You have the length. You have gamma. You have the epsilon for roughness coefficient, and so it is very simple. If I have all of this information, I can calculate hydraulic diameter. I can calculate the area, which is this one minus this one. I can calculate the velocity. I can calculate because I know kinematic viscosity, which is viscosity divided by rho, the Reynolds number. So I know it is turbulent. So I know the kinetic energy coefficient factor. So I can apply full Bernoulli, and I can calculate what is the head in definition of head loss. I don't know what's head loss. So because I know all of this information, they give me the flow rate, heights, etc. But I don't know what is still the head and what is the head loss. So the coefficient of friction, I can calculate it even, because the equation of coefficient of friction in case of turbulent pipes with not smooth, or to use Moody chart by anyhow any one of those. So this is the coefficient of friction, this is the head loss, so head is equal to this one minus this one. So this is the head of the water forces condition. So if we are going to ask me about, okay, there is losses at the inlet. Yeah, if the losses at the inlet, so I assume there is no losses at the inlet. But if somebody told you the key, the losses of the inlet is equal to 5.5, and we know that is delta pressure is equal to K O V square over 2, or head divided by rho G, by the way. So it is K V square over 2G if it is head loss. There is G here, by the way. Huh? So we can calculate it. The head loss is head friction plus head fitting, etc., 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 which is equal to this one. So the head total is, at this case, should be 3.3833 in case of losses of 0.5 for the tank. This is very simple way of using polynomial.